Hi, my name is Shahnawaz. I welcome you in the first lecture or elementary course on metric spaces. In this lecture, we will be studying the definition of metric space and some examples of metric space. First of all, for the sake of motivation, we will attempt to know why do we need metric spaces at the first place. Well, you may have studied the first course on analysis, which is mainly concerned with processes pertaining to limits. The notion of limit can be formulated entirely in terms of distance. For example, we say a sequence xn of real numbers. We say this sequence converges to x if for any epsilon positive there exists a real there exists a positive integer, say n naught, in natural numbers such that absolute value of difference of the terms xn and x, it is less than epsilon whenever n surpasses n naught. One can note that this definition of convergence depends only on the properties of the distance alpha minus beta between pairs alpha and beta of real numbers. There are many other sets of elements for which distance between pairs of elements can be defined, and doing so provides a general setting in which the notion of convergence and continuity can be studied. Such a setting is called a metric space. Now we will begin with the definition of a metric space. Let us consider a non-empty set. A map D from x cross x to the set of real numbers is called a metric if this map satisfies the following properties. So we have property first, which states that d of xy is always non-negative for all x and y in the set x. Then we have property second, which says that d of xy is 0 only if only if x is equal to y. And we have axiom third, which states that distance from x to y is same as d of yx. This axiom is sometimes called as a symmetry of D. And finally the axiom 4th, which says that D of x y is less or equal to D of x z plus D of z y for any x, y and z in X. The map D is called the map D is called the metric on X. Or sometimes the distance function. On X. So why this is called distance function? These four properties are abstracted from familiar properties of distance between pointers in physical space. If you look at the first condition, distance can not be negative, so it is always either 0 or positive, and it is 0 only when the 2 points coincide, i.e. when x is equal to y. Similarly, if you measure distance from x to y, that is same as the distance from y to x, so there is no distinction. Similarly, if we have points x, y and z, so distance from x to y, so if we have 3 points, say this is point x here, this is point y, and this is point z. So distance from x to y, it is less or equal to the distance from xz plus distance from zy. So this is distance from x to y, this is distance from x to z, and distance from z to y. So we know from elementary classes that sum of two sides of a triangle is always bigger than third side. That is why distance of xy is less or equal to distance from x to z plus distance from z to y. And one can see in axiom 4 this is less or equal to sign here. So when this distance, these two distances will become equal, so if z will lie on this line segment x and y, suppose it is over here, then distance from x to z is same as distance from x to y is same as distance from x to z plus distance from z to y. And the pair xd is called the metric space, or we say X is a metric space equipped with metric D. So first of all, we must note something over here. We will often refer to the pointers, sorry, not pointers, we'll often refer to the elements of X as pointers and d of xy as distance between x and y. Let us make a remark here. Suppose XD is a metric space and Y be a non-empty subset of X. And Y is non-empty. The restriction of let us call that restriction dy. The restriction dy of d to y cross y will serve as a metric for y, since it clearly satisfies the space action. It clearly satisfies the metric space actions. So y equipped with metric dy is a metric space, is a metric space. This metric space is called This metric space is called a subspace of X and the restriction dy and the restriction dy is called the metric induced by d on y. So let us do some examples. We have example first. Let X be the set of real numbers. Define D from R cross R to R as this pair X Y over here, it goes to their absolute value of their differences. This is for all X, Y in R. Note that this quantity over here is the real number, so this is a well-defined function. Now, in order to check the axioms of a metric space, one can note that since absolute value of X minus Y is non-negative by definition of absolute value, we have d of X Y is non-negative for all X and Y in R. Similarly, as far as axiom second is concerned, which says that d of X Y is 0 if and only if X is equal to Y, we have d of X comma Y, which is given by definition equal to absolute value of X minus Y, and this is equal to 0 if and only if absolute value of X minus Y is 0, which is if and only if when X minus Y is 0, which is if and only if X is equal to Y. Now, symmetry follows from the definition. If we take d of X Y, which is given by definition mod of X minus Y, which is same as mod of Y minus X, which is same as d of Y X. So symmetry follows easily. And finally, if we have X, Y and Z as real numbers, then d of x y is equal to absolute value of x minus y, which is same as absolute value of x minus z plus z minus y, which is less or equal to absolute value of x minus z plus z minus y, which is equal to d of x z plus d of z y. Now this metric is called, so this d satisfies all the axioms of metric on all the axioms of metric on d, and this metric is known as the usual. So this metric d over here, this is this metric d on R given as d of x y is equal absolute value of x minus y for all x and y in R is called the usual or standard metric on R. So let us try to do another example. Let R power n let x is equal to R power n be the set of all n tuples x1 x2 through xn in R power n. Let x be the set R power n, which is given as all n tuples x1 x2 through xn, such that these xi's are real numbers, where for all 1 less or equal to I less or equal to n. So this is a set of all real n tuples. So for x is equal to x1 x2 through xn, and y is equal to y1 y2 through yn. Define, so these are the elements in Rn. Define d of x y as square root of sigma I runs from 1 to n xi minus yi square and square root. So this is a metric space with this metric. So in order to prove metric space axioms, as far as first axiom is concerned, we have d of x y, which is given to be equal to square root of sigma I runs from 1 to n xi minus yi square, which is a non-negative, since right hand side is the square root of sum of n non-negative real numbers. Now for axiom second, we have distance of xy equal to 0 if and only if square root of sigma I runs from 1 to n xi minus yi square and the square root is equal to 0. That is if and only if xi minus yi square is 0 for all 1 less or equal to I less or equal to n. This is if and only if when xi is equal to yi for all 1 less or equal to I less or equal to n. And symmetry follows trivially, because if we take d of xy, which is given to be equal to by definition square root of sigma I runs from 1 to n xi minus yi square, and it is square root, which is equal to sigma I runs from 1 to n. Now if we take minus 1 out here, and minus 1 square is plus 1, so this is same as yi minus xi square, and it is square root, which is further equal to d of yx. Now it remains to prove the final property, i.e. the triangle inequality. So if z is equal to the n tuple z1 z2 through zn in Rn, then we need to prove d of xy is less or equal to d of xz plus d of zy. For proving this, we need Cauchy-Schwarz inequality. Let's make a remark over here. What Cauchy inequality says: Cauchy-Schwarz inequality it states that if a is equal to a1 through an and b is equal to b1 through bn, b two elements in R power n, then absolute value of sigma k runs from 1 to n a k b k is less or equal to is less or equal to sigma k runs from 1 to n a k square whole power 1 over 2 sigma k running from 1 to n b k square whole power 1 by 2. Now to prove this final axiom, we proceed as follows. Let us consider the expression sigma I runs from 1 to n xi minus yi square. This is same as sigma I runs from 1 to n xi minus zi plus zi minus yi square. Now if we consider this expression over here a and this b, using the formula a plus b squared, that is called sigma I runs from 1 to n xi minus zi whole square plus zi minus yi squared plus 2 times xi minus yi times xi minus zi times zi minus yi. This is further equal to sigma I runs from 1 to n xi minus zi square plus sigma I runs from 1 to n zi minus yi square plus 2 times sigma I running from 1 to n xi minus zi minus yi. Now one can see here we can use Cauchy-Schwarz inequality over here using this expression. So this is, now we are going to replace this expression over here by a quantity which is bigger than this quantity. So this equality over here, it turns into inequality like this. So this will be equal sigma I runs from 1 to n xi minus zi whole square plus sigma I runs from 1 to n zi minus yi whole square plus, now this is equal to sigma I running from 1 to n xi minus zi square and sigma I running from 1 to n so let us write over here plus 2 times this is sigma I runs from 1 to n xi minus zi square power 1 over 2 sigma I runs from 1 to n zi minus yi power 1 over 2, it is square here. So we can replace this over here like this. So this is equal to we can replace this thing over here by this expression. This is equal to sigma I runs from 1 to n xi minus yi square power 1 over 2 plus sigma I runs from 1 to n, not yi, it is zi here, sorry, it is zi here. This is zi minus yi square power 1 over 2 and whole square. Now if we expand this expression, this is exactly this expression over here. So on simplifying, on taking square root on both sides, we'll get sigma I runs from 1 to n xi minus yi square, taking square on both sides we get this is less or equal to sigma I runs from 1 to n xi minus zi whole square power 1 over 2 plus sigma I runs from 1 to n zi minus yi whole square power 1 over 2. Now this is same as d of xy is less or equal to d of xz plus d of zy. So this proves the triangle inequality. So it follows that this space Rn with this metric is a metric space, and this metric space is called the this metric is called the equivalent metric on R. So this proves R D is a metric space where D is called the Euclidean metric.